The problem is from GATE 2017 mathematics paper, question number 29. The problem given is, let C be the simple positively oriented circle of radius 2 centered at the origin in the complex plane. Then 2 divided by pi I times the integration over C z times e to the power of 1 divided by z plus tan z divided by 2 plus 1 divided by z minus 1 into z minus 3 whole square dz equals to. The NPTEL reference to solve this problem is Module 6, Lecture 5 of Complex Analysis. Title of this lecture is Residue Theorem and Applications by Professor P.S. Srikrishna. He is from Department of Mathematics, IIT, Guwahati. Even you can watch this reference video using this YouTube link. So now coming to the solution, we can easily see that this is nothing but a straightforward application of residue theorem. And whereas we have the residue theorem, which tells us that shortly 1 divided by 2 pi I times integration over a curve gamma f of z dz is nothing but the sum over the sum of all residues, the sum of residues of the function f of z at ei, where ai's are nothing but ai's are the singularities of the function f of z inside gamma. So whatever the singularities outside this gamma, that does not matter. In fact, the term here inside gamma matters in this problem. So okay, I'll explain you when the time comes why I'm saying that in particular term. So it is given that the curve C is given C is Z in C such that mod Z equal to 2. As it is given, C is the positively oriented, simple positively oriented circle of radius 2 centered at the origin. And it is given, now we have to calculate the value of 2 divided by pi I times integration over C z times e to the power of 1 divided by z plus tan 1 divided by z plus tan z divided by 2 plus 1 divided by z minus 1 times z minus 3 whole square dz. So now I can rewrite this as 2 divided by pi I, or let me skip this 2 divided by pi I. We can finally multiply with this at the end to the final answer to the integration C z e to the power of 1 divided by z plus tan z divided by 2 plus 1 divided by z minus 1 times z minus 3 whole square dz. So this is our integration. So this I'll split into three parts as integration over C z e to the power of 1 divided by z dz plus integration over C tan z divided by 2 dz plus integration over C 1 divided by z minus 1 times z minus 3 whole square dz. Then since where C is the circle, simple circle, z in C, z in C, such that mod z equal to 2. So the only singularities for these three functions inside this circle only matters. So firstly, let's look at the function tan z divided by 2. We have tan z divided by 2 as sin z divided by 2 divided by cos z divided by 2. So the only by this division, we can see the only singularities of tan z divided by 2 are nothing but the singularities of z divided by 2. Since z divided by 2, sin z divided by 2 is entire, so it does not have any singularities. Are the zeros of cos z divided by 2. Since cos z divided by 2 has some zeros, so those are the only singularities for this tan z divided by 2. Since sine function is entire, so it does not have any singularities for all z. But whereas, okay, let me remove this term. But we have cos z divided by 2 is 0 if z divided by 2 is nothing but 2n plus 1 into pi by 2. So the only zeros of cos z divided by 2 are nothing but these points for the values z divided by 2. At these points only cos z divided by 2 becomes 0, and hence these are the only singularities of tan z divided by 2. So why I am explaining this is, out of these singularities, which points does lie inside this curve C? So to look at that, I'm just explaining the zeros of tan z divided by 2. Sorry, cos z divided by 2. So we have z is from this, we have z is 2n plus 1 into pi. That implies z is 2n plus 1 into pi, and n is any integer. That implies z are nothing but the values pi, comma minus pi, comma 3 pi, minus 3 pi, and etc. So the only singularities of tan z divided by 2 are pi, comma minus pi, 3 pi, comma minus 3 pi, and so on. But out of these, if you observe, now no singularity lie inside this curve C, since mod z equal to 2, and whereas coming to these singularities, we have pi is approximately 3.141, and 3 times pi is more than that, so we can see none of these singularities lie inside the curve C. Out of all these, no singularity lie inside C, and hence we have integration over C tan z divided by 2 dz is equal to 0. In fact, what does this two lines states that tan z divided by 2 is analytic inside C. Since it does not have any singularities, so we can say it is analytic inside C, and hence it has the integration value 0. So, now by just looking at these two integrations, we can easily see the solution. So we have, so integration C z e to the power of 1 divided by z dz plus integration C 1 divided by z minus 1 z minus 3 whole square dz is nothing but, by residue theorem, we have residue of z times e to the power of 1 divided by z at the point z equal to 0. Since z equal to 0 is the only singularity of this function and which lies inside the curve C, so we are considering the only singularity at this point z equal to 0. And whereas coming to the second integration, we have, this is nothing but residue of the function 1 divided by z minus 1 time z minus 3 whole square at the point z equal to 1. Since the only singularities of this function are nothing but z equal to 1 and z equal to 3. Of course, 3 is a pole of order 2. But since that lie outside this circle C, so it does not matter. The only singularity is inside this C only matter. So I'm just considering the residue at the point z equal to 1 only. So hence in total we have this as, so sorry, here these 2 pi I times residues. 2 pi I times this residues. Hence in total we have 2 pi I times the residue of the function z times, I'm just expanding e to the power of 1 divided by z, then we get 1 plus 1 divided by z into 1 factorial plus 1 divided by z square times 2 factorial plus and so on, plus residue at point z equal to 1 of the function 1 divided by z minus 1 times z minus 3 whole square. So and in total we get this as 2 pi I times, so the residue of this function at the point z equal to 0 is nothing but, when we multiply we get 2 times z times 1 divided by z square 2 factorial, we get the term 1 divided by z. So from that we get the coefficient of 1 divided by z is 1 divided by 2 plus, and whereas coming to the residue of this function at the point z equal to 1, this is nothing but 1 divided by 1 minus 3 whole square. So I'll give me a moment. This is by residue of a pole. Okay, let me write in next page. So I'll explain that in a moment. So in total we get this as 2 pi I times 1 divided by 4, that is, sorry, 1 divided by 2 plus 1 divided by 2, this is 2, sorry, 1 divided by 2 plus 1 divided by 2 1, sorry, this is 2 pi I times 1 divided by 2 plus 1 divided by 4, hence this is 1 divided 1 divided by, sorry, 2 pi I times 3 divided by 4, hence 3 pi I divided by 2. But we can ask why it is 1 divided by 3 1 minus 3 whole square as the residue of this function. For that I'm going to give you a formula that if f of z has a pole of order n at a point z equal to a, then the residue of f of z at the point z equal to a is nothing but limit z tending to a 1 divided by n minus 1 factorial times the n minus 1th derivative of the function f of z, sorry, the n minus 1th derivative of the term z minus a whole to the power of n times f of z. So this is the residue of this function f of z, but this formula applies only the singularity is of pole. Since for for this function we can see the singularity is a pole at of order 1 at z equal to 1, so I just applied that formula. Hence in total we have, therefore it is asked the value of 2 divided by pi I integration over c in z times e to the power of 1 divided by z plus tan z divided by 2 plus 1 divided by z minus 1 times z minus 3 whole square dz, and this is nothing but 2 divided by pi I into, as we have derived the value of this integration separately, as 3 pi I divided by 2. So in total we get this as 3, hence the answer is 3.